Here is a long and tedious lecture. Uh, I prepared it for the first time, and therefore there might be some inconsistencies in slides, and material might sound too complicated. But even if you understand 10% or 20, that should be okay, and I think it would be useful. Well, we, we have talked that while low-level details are boring, but they are like a multiplication table. So nobody likes to learn multiplication table, but everybody use multiplication table later. And if something was not clear to you, then probably it is not clear for me. The overall plan of the lecture is presented here. So we will talk about classification of SDN programs and SDN controllers. We will talk about main OpenSDN components and OpenSDN roles. How can you imagine OpenSDN? Which languages are used for OpenSDN implementation? And then we walk from layer by layer through main OpenSDN components and which basic principles are used for their implementations. We will talk about roots propagation, about used protocols, and I will finalize the lecture with a small guide how to download developer environment and how to upload your changes to Gerrit if you decide for example, to fix some bugs or to introduce some features into OpenSDN. First of all, why architecture is needed? Because every day we hear about architecture, but what is architecture? It is a logically connected compound of verified technical decisions, and it is needed to meet some requirements. Actually, requirements go before architecture appears. We have functional requirements from network virtualization, switch and router virtualization, and from network NFV. And we have functional properties and indicators such as scalability, performance, user friendliness. Some properties cannot be specified using numbers, and some properties can be specified using numbers. For example, scalability or performance can be estimated in throughput, in parallel quality, and so on. And when we have these numbers, when we have some predicates, we can formulate a requirement, and from this requirement arise an architecture of a program, or SDN program. Second question which is important is the difference between SDN and SDN controller. SDN is a large solution which usually includes SDN controller and virtual switcher or virtual router and network function virtualization applications and many other stuff. SDN controller is a tool which is used to manipulate routes, configuration of virtual networks, but many authors use them interchangeably. So, and we will do this during this lecture, but actually, if you want to be strict, then you have to separate these two terms. Let's talk about main properties of SDN controller. They are scalability, an ability to increase number of resources horizontally, consistency and ability to keep tables in parallel computations in a consistent state, so they equal or they match each other if we keep tables separated or sharded, for example, like uh, let's remember the example provided by Olga yesterday. She provided example of database sharding, and when we shard our database, we have to keep it in a consistent state somehow. Reliability and security. Reliability is a property to withstand some problems with hardware, with software bugs, and security is a property um, to conserve some security issues. And on this side, on this slide, you can see several works which introduce these key properties, introduce definitions for these properties, and assesses these properties for different SDN controllers. We discussed these properties previously, so I think we can keep this slide. And which types of SDN controllers do we know? Usually we classify SDN controllers as centralized, distributed, and hybrid. Centralized means that all information and processing of this information is concentrated on one computing node. Distributed means that we distribute information or processing of information on different nodes, and hybrid means that we mix somehow both approaches. Well, problems and benefits of both first approaches are known. So when we have a centralized SDN controller, it is, for example, NOx. It is convenience for small enterprises, for campus networks. It's wrongly mentioned here that it has problem with reliability. No, it's probably it's consistent. It doesn't have problems with consistency because there is no data sharding, no data partitioning, but it has problem with scalability, reliability, and perhaps with security. And on the other side, there is a distributed approach when questions of scalability and reliability are resolved, but we also face with large consistency problems, because now we have to synchronize our data. We have to synchronize calculations, and it is all a field of parallel programming, and we encounter regularly data races and deadlocks. And distributed controllers actually fall into two large groups, both logically and physically distributed. It means that we distribute some system logically between computational nodes and physically. And logically centralized and physically distributed means that we think of a control or a program as a logically centralized, but distributed physically. So different part can reside on different compute nodes, but they act as if they are the one program. Modern landscape of SDN controllers is actually very diverse. And I just mentioned several solutions, but you can find, my opinion, you can find dozens of them, maybe 50 or even more. But the well-known OpenSDN, Tungsten Fabric, Open Contrail, OVN, OVS, Open Daylight, RunSDN, NOx, one of the first SDN controllers. So if you want to understand, if you want to study how controllers emerged, and if you want to study first works about SDN controllers, then you can uh, you can study NOx/POX, RU and others. OpenSDN is a physically distributed and logically centralized controller. It can be thought as a hybrid because it still can program Juniper devices, but I don't think that this capability will stay in the future. So probably the second line can be removed. And it is more than a controller. It is a platform because it includes virtual switch, it includes virtual network functions, and it includes diagnostic tools. So it's actually a platform. It uses flow-based granularity, and just recently we have studied why flow-based granularity can be selected by authors because it provides flexible management of packets while saving computational resources. It allows extension of control logic back to compute nodes, and it allows to speed up request for flow, and it delegates state storage management of state information to external data store, namely Cassandra database, which is a key value database. And it was interesting for me to know yesterday that actually soon it might become a vector database. Globally, OpenSDN architecture includes 4 components. And I think during these 3 days, these 4 words were instilled and imprinted in your mind totally. So these components are distributed via 3 planes: management plane, control, and data plane. Management is responsible for global configuration of network. Control plane sends information, and data plane forwards packets. And what makes OpenSDN unique is its closed management cycle. Nowadays, almost all, even I can say all controllers or SDN can forward packets, they can route packets, they can create routes, they can create BGP sessions. However, there is a problem which persists until the present day. First of all, even if we talk about such a uniform program as OpenSDN, a lot of different languages, standards, and protocols are used. So they must be glued and connected somehow. Second problem is about SDN nature, because if we look at this figure, we see that there is a management plane, and we create configuration in language or in alphabet of management plane. And then this configuration is translated into virtual network configuration stored in control plane, and then this information is translated in language or alphabet of data plane. And when we have problems in network, we see diagnostics formulated in language of data plane. And therefore, we must create reverse projection in our mind from problems in data plane to actual configuration in management plane. And actually, this creates a lot of difficulties for network engineers, for developers, and for everyone, because information translates automatically from management plane to data plane. But when we want to understand what to change in management plane to fix problem in data plane, we have to create this projection or translation manually in our heads. And authors of OpenContrail, and now this is OpenSDN, they proposed so-called analytics component, which addresses this issue, which tries to find how problems in data plane can be mitigated by changes in configuration, how they are related. So this closed coupled management cycle might be a solution to problems. And the problem also is also in our nature, because you cannot keep simultaneously more than 7 words. So 7 plus minus 2 words can be in your memory simultaneously. Therefore, all this hard work must be offloaded to computer as much as possible. On the management plane, we have analytics, we have all databases, we have analytics component, web user interface, config, and config database. And this plane manages virtual network configuration on high level, analyzes current state of virtual network, and provides user interfaces for the management of networks. On the control plane, we manage low-level configuration of our virtual network, and we manage routes, creating input information for forwarding plane or for data plane. And finally, on the data plane, we have our vRouter, and which consists of vRouter forwarder and vRouter agent. And our data plane is responsible for applying politics and applying forwarding rules to packets. As you see, we have 3 layers, 5 components, dozen applications, and there is a question how to implement all this complexity. Well, all of this is implemented using different codes. So graphical user interface is implemented using JS. Python is used for management plane, for config, for input data management, C++ for operative database management, C for packets forwarding, and so on. And we also need some kind of gluing technology, which is called interface definition language. Here we use Apache Swift version, which is called Sandesh. And we also use C and C++ for different purposes. C is used for performance critical parts of the code, only for data plane and for forwarding. And C++ is used for logically complicated parts of code, like controller, vRouter agent, and virtual DNS server. As you know, different languages provide different advantages, and usually we can build such a hierarchy or ladder where we have assembler language at the lowest level, and this level provides us highest performance and memory and best memory usage. And at the upper level, we have such languages as Python or Java. Usually, the closer language to hardware, the higher its performance. But this also increases risk of errors and severity of consequences. So, as you know, It's very easy to ruin program or computation if you have a code on C or C++, and programs on Python or in some domain-specific languages are easier to use, but they have some performance problems. Languages can be also divided by using next approach. So there might be machine code, sequences of zeros and ones, assembler, which is actually mnemonics for binary code. So assembler is very close to binary code, and that's why it's very efficient. Then go general purpose code programming languages like C, C++, Fortran. Then go in interpreters, which don't need which don't need translation into object code. And there is a specific domain specific languages like LaTeX. If you ever saw scientific papers or serious journal papers, they are usually prepared using such languages as LaTeX. And I also gave as an example language Relap 5, which is used for nuclear energy management. And also languages can be separated into declarative and imperative. Within imperative languages, we specify steps we need to do in order to achieve some goal. And within declarative languages like Prolog, Lisp, we specify which results we need, and then program gives us results according to its internal rules. And you might ask yourself, why am I dedicate so many time to classification of languages? Because of the next. Because OpenSDN can be thought of different roles. You might have seen this figure, yes, if you project light on a cylinder, and you can see a circle on one wall, you can see square on different wall, but actually this is a cylinder. And the same for many things in life. You can think of OpenSDN as a compiler, and it is a compiler. It is a language. You can think of OpenSDN as a network system, operating system, and a virtual router. And thanks for great presentation, dear, where you explained in details how OpenSDN works as a virtual router, because it really adds a lot to this talk. And these roles can be also considered as levels, and we will see how this how this implemented actually. If you look into Contrail Architecture Guide, CHAP, you will see a chapter, Scale Out Architecture and High Availability. And their authors consider OpenSDN as a compiler that compiles high-level data model into the low-level one. Well, first of all, I think it's more interpreter, because there is no translation into object code. But if authors call it compiler, we will call it compiler. And usually each compiler has several steps like pre-processing, translation to object code, and linking. And our OpenSDN compiler also has its own stages. It has a stage of translation from high-level to low-level model, and it has a stage of translation from level model to low-level model to forwarding information base, which is used actually for forwarding packets. And yesterday we saw that actually the router forwarder acts like a processor. Yes, it has several tables, and it processes these tables in some kind of fetch and execute cycle. And high-level and low-level model are actually just a language definitions. So they are not an actual state. And when we speak about actual state, then configuration state corresponds to high-level model, and operative state corresponds to low-level model. If some of you studied, for example, object-oriented languages, you know that there are classes and there are instances. So data model is a class, and state is an instance. And now we can describe our OpenSDN as a language. It's a declarative programming language, obviously, because we do not specify algorithms how to process packets. We only specify what we want to see. We specify configuration of network, we specify policies. So it's a declarative language. I call him interpreter, but authors call it compiler. And it provides instruments to define virtual networks. So it is a domain-specific language. This language is needed only for network, for creation of virtual network. And it provides virtual switches, and it has tools for failures diagnostics. But actually, OpenSDN is a network operating system too. It provides interface to modify network, to manage network, to distribute resources, to manage security, to manage authorization and identification. And the first notion of a network operating system was introduced in the work dedicated to NOx controller. That's why I paid attention to this publication in the previous lecture and at the start of this lecture. So if you want to understand the very first principles which were used to create first network operating system, which was to derive the idea of network operating system, you should refer to this work. This is a pioneering work. Or you can make a shortcut, open gigs for gigs, and they also give a great description, list of functions for network operating system, creation and management of user accounts on the network, controlling access to resources on the network, communication services between devices network, troubleshooting, configuring and managing resources on the network. It is all what OpenSDN does. Therefore, it is network operating system. Looks like a duck, walks like a duck, and then it's probably a duck. And finally, OpenSDN is a virtual router because it allows us to manage routes L2, L3. It can pair with BGP peers, with other BGP routers, and it can forward packets. So it's a virtual router on top of network operating system. Now, when we learned how to look at OpenSDN from different points of view, we can study how data flows inside OpenSDN. And actually, there are three streams of data. And we remember that we use flow for a different entity, therefore I use stream. That's why English is good, because it has many words for similar senses. So there is a packets data stream, routes data stream, and configuration data stream. Packet stream is just a packet that goes from one interface to another and goes between hypervisors, and we manage how these packets go from interface to interface. The routes data stream is the information which programs how these routes how packet streams are organized. This information propagates from controllers to the router agent, and then from the router agent it propagates to the router forwarders. And we see that controller is physically distributed, so we can have several controllers, but controller is logically centralized. So any router agent connected to two of controllers actually think of these controllers as a single entity. And the router agent are physically distributed and totally physically distributed, so they are not centralized. And finally, there is a configuration data stream which programs routes data stream. This data stream starts at REST requests, then it propagates to config and database component, and then it propagates in the direction similar to direction which is applied to routes data stream. And I tried to put roles of OpenSDN and streams on one plane. You see roles on the horizontal coordinate, and you see planes on vertical coordinate. And we see that we occupy lower triangle. So usually we have a configuration, compiler processes this configuration, then data stream flows and the role of OpenSDN switches, it becomes operating system because it distributes this configuration to other devices, virtual or physical. Then our configuration becomes routing information or data stream, and roles switches together. So OpenSDN becomes virtual router on all three for all three streams of data. And the rest of the lecture will be dedicated to questions how all these components, roles are implemented, how packets are forwarded, and so on, and how different parts are linked together. Everything starts with REST messages, which are used to program a high-level data model. REST messages can be of different types, like create, read, update, delete, and link. And these REST messages have specific structure, which is governed by some standard. You can find standards for REST protocol. And we can specify REST request using curl or using web user interface. So actually, when you hit the button in user interface, actually each changes in user interface are translated into REST requests. Requests are stored into two databases. First, they are stored in persistent database, which is called Cassandra. Cassandra is known to be used in, for example, in Netflix and Instagram. That's why their icons are here. And after translation of this information from persistent database into operative database, and we know now that OpenSDN acts as a compiler to translate this request. They are stored into operative storage, which is actually a collection of tables inside memory. Translation happens inside logically monolithic applications such as controller, DNS server, config API. I think we can skip this slide, or maybe just a couple of words. So Cassandra stores value in a key value approach. So actually we have two tables. One table has a mapping between type of element, type of network entity, and its identifier. And second table actually stores mapping between identifier and element property. Then this information, the information from Cassandra, is translated into ifmap database. Ifmap format is also governed by standard that was produced by trusted computing group. I suppose this group is a joint team of several companies, because I saw names from Juniper, from Cisco, and other networking companies as authors of documents. And this ifmap database is represented actually as a graph where objects correspond to entities of virtual networks, and references between these objects are represented as edges. And finally, this ifmap database is transferred into operative database, and which consists of tables. Tables are partitioned along CPU cores. So it's a different approach to sharding. Yesterday, Olga about sharding, which partitions computational efforts among different compute nodes. And in pure partition without sharding, we split computational efforts among different CPU cores using, for example, multi-threading libraries. Each partition contains entries actually as a tree, and each entry has several states. Ifmap database is represented like a graph, so it allows us different approach to cross it. For example, we can cross it using BFS, breadth, breadth, I forgot English word, proper English word. So we can go in depth and we can go in breadth. But how it is translated in English properly, I don't remember. And there are at least 5 applications of graphs in OpenSDN, and we will see how they applied right now. First of all, graphs are used to specify data model. Data model graph is a central idea which is used in OpenSDN actually. It's a directed acyclic graph, a kind of polytree, which has a single root and several children. And references between nodes can be of 2 types. So you can see edges with solid lines and with dotted lines. Solid lines are edges for members, and references, which say that they just know about each other. References is a second type of edges. And here is a simplified version, and I tried to display a full version of data model. It is much more complicated, and as you can see, it is even doesn't fit onto screen. And if you want to watch, if you want to watch objects, states created from data model, you can use introspect, for example, in user interface, where you can open each table one by one. Then our controller and also vRoute agent has their own small graphs, which are hard-coded into their code, and they used to cut configuration or to cut trees, and also they are used to propagate configuration information. I want to give an example. What does it mean, propagation of configuration? It means that, for example, if interface is changed, then we must decide which elements must be updated if one element is changed. And this task is solved using configuration propagation graph. And another task is creation of graph cuts. When controller receives this full graph from config, it must decide which part of this graph must be sent to vRoute agent on a specific hypervisor. And we have a special list or special policy, which is actually represented as a graph, which decides which elements are sent to specific vRouter agent. For example, a polyforest of graph of configuration propagation graph. Also, red-black trees extensively used for storing information like routing information base, if map tables, and many other data is stored using red-black trees. Patricia trees are also frequently used for iNet unicast routes. It's obvious because radix 3 are good for storing prefixes. And finally, state machines are also graphs, and they are represented using a very interesting C++ semantic based on templates. We will not consider this today because it's an additional topic. But nevertheless, they are used to represent these graphs. And this is an example of BGP session state machine. And this is an example of XMPP session machine, which I extracted from the source code. And controller can be regarded as the central point for routing information base because it sends portion of its tables to the route agents. And it works as a pipeline. So it receives some kind of information, it processes this information, and then it distributes this information with its peers. And we remember that peers of controller can be of three types. The route agent are peers of controller. In other controllers, because we remember that controller is a physically distributed entity. Each controller instance shares its information with other controllers to have all tables consistent, to have all tables equal on each controller node. And controllers actually interact with other BGP routers from other networks, from other data centers, and so on. For example, you can see that each controller instance is connected with other controller instances, and it is connected with other config instances. So config is looks like logically centralized, but it is distributed. And finally, you can see here the pipeline for processing of route information in controller. So for this pipeline corresponds to data obtained from the route agent. So when the route agent sends information to controller, it is processed in step 1. Then this information is submitted into table. Information is inserted into table. Then there are special classes which creates aggregated version of information from several tables on one instance. And then there are special classes on steps 5 and 6, which are responsible for sending this information to all peers which might be interested in this information. Main parts of the router agent are ifmap database. So like a controller, it has a ifmap database. It has operative database. It also has a bunch of servers and proxy servers like metadata proxy, introspect, and so on. And it also has parts associated with the router forward synchronization. Main elements of routing information base is virtual network, is an entity which specify policies. Then goes virtual routing and forwarding, is a member which specify how to route and forward. Within this VRF, we can have several route tables, and each route tables have several routes, and each route has a prefix, is a address, as a destination address where we want to get, and each prefix can be L3 or L2. And each route, in addition to prefix, has a path consisted of next hop and peer. Peer actually is the origin. This is a very strange definition because peer means origin. If you look into the route agent tables, you will see that some routes, for example, have peer local VM port. It means that this route or this path has been generated locally on this hypervisor. Or you can see peer external, and it is called BGP peer, and it means that this path was created somewhere else and it was transmitted via, for example, BGP protocol. So actually, when you see peer in the route agent routes, you should know that actually it is a source of this route. It denotes who created this path. And you can see here how tables are actually distributed among several hypervisors. For example, let's imagine that we have 2 controllers and we have 3 hypervisors. Then we have orange, green, and violet hypervisors. And each hypervisor has its own agent, has its own and has its own vrouter forwarder. And it means that, for example, we have 4 virtual machines on Orange hypervisor. It means that each virtual machine will create its own root records, and they will be inserted into agent routing information base. And agent will send this part of its table to controller. And you can see that this part of agent routing information base is transferred to controller table. And the same applies to other hypervisors. This part of green hypervisor translates to middle part of controller tables, and this part of violet hypervisor routing information base transforms to controller. And then controller, when controller gathered all information, it reflects this information back to other hypervisors. That's how other hypervisors know about routes to their neighbors. So this part of green hypervisor on controller is transferred back to agent and is transferred back to agent, to violet agent. And for example, this part of violet hypervisor RIP is transferred from controller to the table on orange hypervisor and to the table on green hypervisor. Finally, there is one important mechanism which is used in OpenSDN, and it is called route leaking. This process or procedure is responsible for exchange of data between tables. So when we have 2 tables and one line or one record from table 1 is copied to the table number 2, this process is called route leaking. So even though it might sound mysterious, actually it's just a process of copying entries between 2 tables. And here is just an example. For instance, we can copy a record from table 1 and from table 2 into table 3, and it means that routes from table 1 and table 2 are leaked into table 3. And many components of OpenSDN uses this mechanism. For example, VXLAN control plane implementation uses routes leaking. VXLAN as a standard involves 2 parts, actually, data plane and control plane. As a data plane, VXLAN is about adding one more external header, and as a control plane, VXLAN is about redistributing routes to different VTEPs. And the default mechanism of routes redistributing is called flood and learn, and it requires a lot of resources from virtual networks. Instead, authors of Contrail and now OpenSDN decided to use some kind of central authority or PGP approach when we redistribute these routes centrally using controller. And this is actually we redistribute this, we copy routes or we leak routes on vrouter agent, but then these leaked routes are gathered in controller. But the principal idea is simple. We copy routes from one table to another. Example is shown here. For example, we have several several networks with each VRF table connected to one VXLAN router, and it means that we have a fourth table to which we copy routes from each of these connected bridge virtual networks. Finally, when we have routing information based on our vRouter agent, we copy this information as a forwarding base into vRouter forwarder. And those of you who reached this figure yesterday might remember it because it depicts main parts of forwarding information base in vRouter forwarder. So forwarding rules are stored in inet routes table and bridge routes table. These tables reference next hop tables, and they are also associated with interfaces tables, which are associated with VRF tables. So each interface can belong only to one virtual routing and forwarding, or can belong to one virtual network. And as I told you, OpenSDN is a network operating system, and it provides services for application of high level. For example, there is a VDNS service, which is actually a separate application that runs on top of OpenSDN, and it uses Cassandra database for its own purposes. And it also talks with other OpenSDN services like vRouter and virtual machines. And all these elements are glued using a single interface definition language, which is called Sandesh. And Sandesh is just an extension of Apache Swift. It has two main goals. First goal, creation of single interfaces for different languages, because if we have some part written in Python, some part in C, some part in C++, we need some tool to synchronize interfaces between different languages. And Apache Swift do this work for us. And second goal is a standard or protocol for data exchange between different components. If you want to understand how to work with Apache Swift or how the process is organized, you can refer to the tutorial mentioned in this link. Basically, it is also a kind of layered library where you select how to transport data, how to encode data, and socket type is how to identify pairs of communication. And here is an example of interface definition. For example, we have a structure work. It has 4 fields. And after parsing this interface definition, we will have separate interfaces or interface classes or definitions in all languages, which will enforce types specified in this IDL. So we will have, for example, if we want to have 32-bit integer for num1, then Apache Swift will enforce this type of field for all languages we use in our components. While Apache Swift is relatively mature and old library. It also has rivals or replacements. So actually, it can be replaced by other ideal or RPC programs like CAP and Proto and others. Sandesh extends Apache Swift language, and it adds additional functionality. Additional functionality allows us to inspect state of our SDN controller, SDN without agent, in different ways. For example, there are UVE, user visible entities, tracing, and logs. UVE is a state which is polled regularly from different components. So we can poll components and ask about their state. Tracing actually is a ring buffer where we store log information. So if we want to debug a program or if we want to look about some intermediate results, we can save these results into ring buffer and extract them using tracing. And logs are simply logs which are stored on persistent storage like hard disk. And here you can see these types. They correspond to trace object corresponds to trace. UV is not presented here, but there is a UV type which corresponds to UV inspection and so on. And since Sandesh is used for gathering information, there must be someone who generates information, generator, and there must be a collector, someone who collects information and someone who gives this information to us. Therefore, all applications in OpenSDN can be generator or a collector. And if you want to understand how to inspect applications of OpenSDN, you can look into its source code. There is a file vns.sandesh, and this file contains ports for all services provided by Sandesh. Finally, our OpenSDN uses external libraries. It uses Apache Swift for Sandesh. We discussed it just recently. It also uses Intel TBB for trading management. It uses Boost library for memory management, for strings, yes, for memory, for strings. It uses for Boost, for example, for specification of state machines using graphs and for many other tasks. Also, bind9 DNS server is used. Scones tool is used for managing source code. And DPDK library is used to accelerate package switching. We use about 10 protocols and formats to exchange data. So main standards which are used in OpenSDN are REST, IFMap, BGP, Netlink for communication between agent and forwarder. Shared memory is used. JSON format is frequently used, XMPP, BGP format, Sandesh, and XML. The code in OpenSDN it is tested mainly using J tests. First of all, this all concerns controller and VRoute agent, but other part might also use gtest. And for VRouter forwarder, there are self-written PyTests, which were written partially by Pragmatic Lab and partially by Juniper. Main repositories of OpenSDN are community, where you can find exhaustive list with description of each repository, docs containing documentation, but it is somehow outdated, so it really needs more work to finalize it. And VRouter and controller repositories contain information, contain source code for VRouter and controller components. And if we speak about numbers, OpenSDN source code counts about 800,000 lines of C++, 350,000 of Go, about 300,000 of Python code, and about 70,000 lines of C code. And if we add all of it together, and if we decide that someone produces about 70 lines of code per day, this is actually a good performance, because coding is not just a typing. It is also about debugging. It's about testing, checking. We can achieve that this program can be written in 92 work a year. So if we gather 100 coders, developers, and if we put them into one room, they probably will finalize it in 1 year. But if we gather them, there is a special container which is used to prepare this complicated development environment. This container is called tf-dev sandbox, and it is stored in repository tf-dev-env. It definitely works on Rocky 9.5. It definitely works now on Ubuntu 22. I checked this just a week ago. And well, it has a relatively relatively fresh documentation, so you can open readme.md and follow steps to run this container. But since it compiles 1.5 million lines of code, this will take about night on notebook. Yeah. If you have 4 CPU cores. If you have 16 or 32 CPU cores, this will take several hours only. Main stages are listed on the slide, and they are also listed on README. Finally, if someday you decided to contribute a project, there is a guideline. There is, or somebody in your family decided to contribute to the project. There is a contribution guideline which involves several major steps. First, you have to log in to GitHub, and you must create a public profile with public email on this profile. So email must be visible to everyone. Then you must install Git on your system and obtain SSH key. And then you can link your Gerrit account with GitHub account and install Git review on your local machine. And probably this is all. 20 минут.
Have a question มีไหม มีไหมฝั่งนู้นมีคำถามไหมฮะไม่มีอ่ะโอเคฮะโอเค โอเคฮะก็เดี๋ยวเบรกกัน10 นาที15 นาทีแล้วเดี๋ยวกลับมาทำติวโตเรียลกันต่อครับฮะ
Since these tutorials use the same base, there is no need to recreate virtual machines again, and all steps are written here. And it looks like maybe it will be more efficient for us to try to try this tutorial in a different manner. You will follow steps from browser, and if you have any questions, you just ask me and I will help you. So you can select any of this tutorial, and if you have questions, just ask me.